Hello, everyone. I hope you're all doing great. I am Manoj and your host for the session. Today, we will be studying a topic that resonates with anyone who's ever tried to find a balance in the complexity of modern software development. This session is all about navigating the intricate landscape of today's software while striving to keep things simple. As applications become more feature-rich, the challenges of developers and testers multiply. Longer build times, stretched feedback loops, and the constant pressure to deliver can make managing complexity seem like a losing battle. But what if there is a way to turn the tide? Leading this session is someone who knows this terrain better than the most, Simon Stewart. Simon has been at the forefront of Selenium project for over a decade and has significantly shaped how we automate browsers today. With a career that spans stints with industry giants like Facebook, Google, ThoughtWorks, and most recently, he's been focused on building tools that simplify developer experience at a very well-known Californian tech company named after fruit. But before we move on and hand over the stage, a few suggestions to all our participants. Please encourage speaker by using emojis below, and I can see you're all doing it great. Keep that going. At the end of the session, we will be taking questions, so feel free to add those questions in the Q&A section. Now, please join me in welcoming Simon Stewart as he enlightens us on the complexity of simplicity. Over to you, Simon.
Thank you very much for that introduction. I'm just going to share my screen. Can you see that okay? I can see it there. Great.
Yeah.
Fantastic. So thank you for that kind introduction. It's a real honor to be here at TestMu, and I'm really happy to see you all here. I can see the chat flying by. It's fantastic. In this talk, we're going to be exploring the ideas of complexity and simplicity and thinking about what we mean by those words and how it affects our day-to-day lives as software engineers and testers. Now, I've been working in software engineering, as Manoj said, since the late 1900s. So I've seen and written an awful lot of code. I've also been involved with open source for nearly as long. I think it's fair to say that I've experienced an awful lot of complexity at first hand and also my own fair share of simplicity. Now, before we begin, perhaps it's best to take a step back and think about what we actually mean by simplicity. The first place to start is with a basic definition we can use for the rest of this talk. I spent a while looking up and thinking about the meaning of the word simplicity, but I also wanted a definition we could explore further in this talk, and dictionary definition didn't quite fit. Fortunately, we have the concept of an antonym. And an antonym is a pair of words that mean the opposite of each other. Think war and peace, or thick and thin, and you've got the idea. When we speak of simplicity, we almost always frame it as the absence or lack of complexity. That is, for most of us, simplicity and complexity are antonyms. Put another way, if something is very complex, it's not simple. Similarly, if something is simple, it lacks complexity. Now, this is a great starting point and gives us the first dimension to think about simplicity. But I'm sorry to say this definition lacks the nuance we need to have a meaningful discussion about complexity and simplicity. Now, sometime in the 3rd century BC, there was this Greek chap called Aristotle. He was, to put it mildly, a pretty clever fellow. Sure, I mean, Archimedes came up with some nifty ideas about helical screws and did some unlikely things in baths, and Pythagoras figured out some cool things about triangles, but did you know that Aristotle made a significant contribution to computer science and engineering? You see, Aristotle had this concept of essential and accidental properties of a thing. Wikipedia helpfully defines this as an accident is a property that the entity or substance has contingently, without which the substance can retain its identity. It's a bit complex, but I mean, really put another way, an essential property is something without which something is not the thing it's meant to represent, whereas an accidental property is something that isn't a core part of the definition of that thing. As an example, whether or not I speak a particular language is an accidental property of being human, whereas being mortal is an essential property. Isn't that right, my fellow mortals? Now, I'm no great philosopher, but Jonathan Lips of the Appium project is, and I am absolutely certain that he came up with something far more interesting and compelling as an example rather than human mortality. However, I think it's enough for us to have this concept of accidental and essential properties, which was one of the great innovations in thinking that Aristotle came up with. Now, you would quite naturally be right in asking what on earth this has to do with computer science. I'm glad you asked. In 1986, Fred Brooks wrote a paper called No Silver Bullet, Essence and Accident in Software Engineering. This is, by the way, the cover of his other book, The Mythical Man Month, which is probably his better known work. For those of you not familiar with the stories of the supernatural, a silver bullet is one of the very few weapons that are effective against werewolves. Sadly, Fred Brooks wasn't writing some early Harry Potter fan fiction about Remus Lupin. He was instead referring to the idea that a silver bullet is a simple and almost magical solution to a difficult problem. In this paper, Fred Brooks argues that it's unlikely that we're to see programmer efficiency increase to the same order of magnitudes as improvements to hardware have increased our computing power. The first sentence of the paper reads, all software construction involves essential tasks, the fashioning of the complex conceptual structures that compose the abstract software entity, and accidental tasks, the representation of those abstract entities in programming languages, and the mapping of these onto machine languages within space and speed constraints. So you see, we can add a second dimension to our definitions of simplicity and complexity. We can say that any problem has a certain amount of irreducible complexity in it, and even the simplest solution may end up being something that appears to be complex and complicated. That is, any solution to a problem must address the essential complexity of the task and must strive to reduce its accidental complexity. Yeah, nice bit of theory to have, I guess, but how do we apply this to our lived experience as software engineers and testers? Oh, let's take Selenium as an example of accidental and essential complexity. Worked in it for many years. I'm very familiar with it. I hope most of you are too. If you clone the repo, and you are welcome to, you'll find that it has all the languages we support in a single tree. Why is that? It's because there's a lot of shared code and utilities. We could lift that shared code into its own repo and then use something like git subtree to pull that in and use it. And that would allow us to separate things out. But if you've ever tried to manage code across multiple repos like this, you'll have experienced the sheer horror of managing changes. For us, a single repo provides the essential complexity of access to the code without the accidental complexity of having to manage multiple different repos. That approach works well for us, but since we don't have organizational boundaries or political issues to contend with, and we're a relatively small team. So we have a single repo, but now we've made our CI builds more complicated. We've introduced some accidental complexity. A traditional CI build will have a flow that a change in the repo is detected, it's cloned, and then a series of steps are performed sequentially. These steps are typically things like linting, compiling the production code, running the small tests, then running the integration tests, and finally, the end-to-end tests. There might be fancy features like fan out and fan in used to speed things up, but by parallelizing some of these pieces, but that's the gist of how things work. The problem is that with a single repo, if someone changes the Ruby code, we likely don't need to do anything to verify that the Java code is still fine. If someone updates a README, do we really need to run all the tests? The naive thing to do would be to filter by language and then only run the subset of tests written in that language, but that approach doesn't work since we share chunks of JavaScript and other code between languages. We'll discuss how we've solved this accidental complexity later, but for now, it's enough to notice that by choosing one approach to reduce accidental complexity in one part of the system, we've introduced more accidental complexity into another. Now, who's to say what's simple? I mean, that depends, doesn't it? What does it depend on? For a start, it depends on your level of mastery of the problem being solved and the tools being used to solve it. If you ask me to solve a problem in, I don't know, bioengineering in a fully equipped lab, I'd be very tempted to say that any solution we came up with is complicated. I'm not a bioengineer. But if I was, I'd be assessing the solution we come up with in a completely different light. Similarly, I have the great pleasure to work with people of various skill levels and experience, both professionally and in open source. Code that reads well and looks simple to me is sometimes an unfathomable mess to other people. Worse, I'm sure we've all had that feeling of, picking up some code or a system that we used to be familiar with, only to find it an oddly alien and uncomfortable place. Our gauge of how simple something is depends very much on our current familiarity with the problem domain. What a nightmare. Tomato, tomato. Even though it's the same thing, there's no single way of looking at things that's correct for all people. I think the best way to summarize this is with Kernighan's law. Everyone knows that debugging is twice as hard as writing a program in the first place. So, if you're as clever as you can be when you write it, how will you ever debug it? Oh, great. But how do we apply this to our day-to-day experience? Well, the first bit of advice is to avoid being clever. When presented with a problem, just solve that problem, not the generic case you see within it. Now, people working in software are natural problem solvers. We like to come up with solutions that can be applied more than once. It feels wasteful, right, just to do one specific thing for one specific problem, and you can see there's a general solution lying underneath. The problem is that we sometimes see patterns where they don't exist. We should wait until we've got a few examples before attempting to come up with that general solution. Put another way, when it comes to frameworks, we should extract rather than develop. As an example, the very first WebDriver APIs were the end result of having applied the learnings and experience from many different projects. If you looked at them, they seem pretty simple, but they were the distillation of years of experience. Which leads me to this meme, which I'm sure many of you have seen before. It's a pretty common one. It describes the kind of thing you see. The first solution to a problem seems simple, but as more edge cases and examples are thrown at it, the solution needs to become more and more complex. After all, the initial solution didn't fully address the essential complexity of the problem. But while we're growing code and solving problems, we occasionally take wrong turns and our understanding evolves and grows. That means that at some point, we fully address the essential complexity of the problem we're solving. But along the way, we've introduced a whole heap of accidental complexity. But now we have the understanding in place, we can see what needs to be done. After we've removed the accidental complexity, we're left with something that quite often looks like the initial simple solution. By the way, this is why it sometimes feels so much easier to throw an existing solution away and replace it with something new. We can take our current understanding of the essential complexity of the problem and apply it instantly with far less accidental complexity. If we do this with new tools, it can seem natural to credit the tool with our better understanding and accumulated experience. But that's not the case. We're just being able to apply the essential complexity and solve that more directly. And that brings up an interesting point. You see, not only does someone's definition of complex or simple depend on whether the complexity is essential or accidental, and that depends on their level of mastery of the domain the problem is in, but we also need to take into account the goals of the solution we're looking at. Perhaps this is best illustrated by the evolution of programming languages. When I was at university, they spent the first year teaching us C++, because that was the language that was most prevalent in the industry back then. It's true, folks, I really am that old. C++ was, and indeed is, a powerful and capable language. It supported object-oriented programming, and C++ had reified generics and supported multiple inheritance, both of which allowed amazing levels of expressiveness. The standard library had many useful utility types and made life a lot more pleasant. Now, if you're a programmer, you've already picked up on the ++ bit of C++'s name. It was an evolution of C, and C++ still shows its roots. It had features like a preprocessor, which let you define macros that would expand inline into chunks of code. And you could use defines to optionally choose to reduce duplication and include particular parts of the codebase at compile time. It was also close to the metal. You had to manage memory allocations and deallocations yourself. But James Gosling had been working hard at Sun on a language originally called Oak, but now better known to us all as Java. The goal of Java was to make C++ simpler for developers by removing some of the rough edges from C++. After all, there was a large body of professional software developers who were already familiar with C syntax, but were kept falling into traps laid by the language. For example, memory management in C++ is notoriously hard to get right. So Java introduced garbage collection. The preprocessor was nice, but it added overhead when compiling code, and it made it easy to obscure details that should have been made more obvious. Out it went, along with macros and defines. Java also introduced better mechanisms for sharing code as libraries and ways of calling code that wasn't yours. And one other thing. With Java, you didn't need to worry about the architecture or operating system of the machine your code would ultimately run on. Write once, run anywhere, as the old saying goes. All these changes made Java a very attractive option, and for decades it was rightfully been one of the most popular programming languages out there. But Java isn't without its problems. Over the years, Java has evolved to be ever more expressive and powerful. The introduction of generics in Java 1.5 opened the door to solving a lot of problems more elegantly. The new I/O, the NIO package in Java 7, allowed efficient network servers to be written. Java 8 came with lambdas and streams, which made it easier to code in a more functional style. Java 11 had more features like, type inference for variables. And by the time we get to Java 17, features like switch expressions and records had appeared. And the downside with all of these features? There's a lot more to learn when you get started, and things like generics can be hard for experienced developers to get right. There's clearly a lot of room for improvement, and over at Google, Rob Pike was working on something simpler than Java. One thing to do was to lower the barrier of entry by keeping syntax as basic as possible. By removing exceptions from the language, the flow of control for a function becomes clearer, at the cost of requiring a lot more error handling code to be written. But that error handling code always seems to follow a well-known pattern, so although it's verbose, it's also clear. Multi-core CPUs were an exception when Java was invented, but were the norm by the time Go came along. So Go has features that make dealing with multi-threading and concurrency easy, and they're baked into the language. Where Java knocked the rough edges of C++, Go made Java simpler, especially for developers new to the language. And that caveat, especially for developers new to the language, that's important. Why? Because it highlights that we can make a choice about where simplicity and complexity live in our code bases and workflows. The conscious placing of complexity within a system allows us to make trade-offs that work best for us and the environments and teams we're working with. For example, Go chose to push the complexity of error handling into the regular flow of control in a function, which makes everyone pay the cost of thinking about errors all the time. On the other hand, Java can use exceptions so that the happy path through a method is clear, even if it takes more effort to understand what happens when things go wrong. I mean, especially when unchecked exceptions enter the picture. Put another way, simplicity and complexity need to be evaluated against the design goals that someone is trying to achieve. For some, the basic readability of Java's happy path approach may be simpler, whereas the clarity of Go's approach may be simpler for someone else. Neither approach can definitively be said to be better than the other, but you can be sure that fans of one will claim that the other is unnecessarily complex. Perhaps another example will help. You may not know it, but there are at least 2 different ways for a browser to intercept and amend network calls. One way is to use the Chrome debugging protocol, or CDP, to its friends. Another way is to make use of new functionality provided by the WebDriver BiDi, which is a new W3C spec. Now the question is, which is better to use? And does your browser support it? You could pepper your code with checks to see whether or not one or the other approach was available, and then have a series of if-else statements. It gets very messy very quickly. However, within Selenium, we have a class called Network Interceptor. Just pass out a WebDriver instance, and you can start intercepting network traffic, as the name suggests. It will make the choice of the underlying technology to use, and the API it offers hides the complexity from users. The network interceptor, in this case, is an example of don't repeat yourself in action, and how we can use that to push complexity around in our code base. We took the repeated blocks of code where we had to make a choice and pulled it all into one place. It's a pattern I've seen repeated endlessly and is highly effective. It was the application of DRY, don't repeat yourself, that can lead to the creation of page objects or an implementation of the screenplay pattern. You take the code that repeats endlessly, pull it into one place, and apply your preferred design approach to it. And take a note there. Once again, we're extracting to a pattern rather than just implementing it blindly. So there you have it, the many dimensions of simplicity and complexity. We can view simplicity as the absence of complexity. We can view complexity through the lens of being essential or accidental, and we can refine that view by thinking about our own understanding of the problem and the tools we use, as well as the goals we seek to accomplish. With that clear view in mind, we can choose where to place complexity in our code and workflows. And now, with that definition in place, let's think about some of the other problems we're trying to solve. The goal of software development should be to get a new line of code into production as quickly, as safely, and as cheaply as possible. After all, if someone can't use our code, it might as well not exist. We can measure the time from when someone initially commits their code to when it's in production, although that start time might be a little fuzzy. I mean, is it when the coder starts typing, when the first commit is pushed, when the code starts to be reviewed, when the story is planned? But I think we can all agree that by quickly, we mean whenever that start time begins, it should be as short as possible until the code is in production. And what do we mean by safely? I like to loosely define safety as confidence that a change doesn't break anything. That doesn't mean that the change is entirely perfect. After all, like, defects slip through the net all the time. It just means that we have a sense of confidence that a change won't make our systems worse. It's not a perfect description, but it helps to guide some of my thinking. This definition also leaves open the question of what can break with a change. There are obvious things that spring instantly to mind, such as a feature not working at all or having unforeseen and undesirable side effects. I don't know, using too many resources, accidentally wiping data, or being slower than is useful, for example. There are also less obvious concerns, such as how we interact with other parts of the system, or how changes in APIs may cause code that depends on us to fail to compile. If you're using services, micro, macro, I don't mind, whatever makes you happy, then the contracts between those services are also places where we can expect and frequently find breakages. The worst possible time to find out about breakages is in production. For applications and services, what production means is clear. For libraries and shared utilities, production may be the point where someone else takes a dependency on that code. That is, when someone updates the version of the library to the recently released version and tries to recompile. Depending on how frequently dependencies are updated, there may be a lag of months before there's proper confidence that a change is safe. And finally, what do we mean by cheap? For the sake of this talk, I don't necessarily mean in financial terms. I mean how expensive something is in terms of engineering hours. Back in the old days, we used to talk a lot about the cost of change curve, which posits that finding and fixing issues earlier in the development lifecycle is cheaper than doing so later on. I think that's an axiomatic truth, even if the exact details might be something we can quibble over. Put another way, the longer the feedback loop, the more expensive it is to react to the results of that feedback loop. Shorter feedback loops are cheaper. With a compiled language, the earliest point we can get feedback about a change is at compile time. Change an API, and the code won't even compile, which is magical. The next cheapest way is to run the tests in our repo. Assuming those tests pass, we then need to publish snapshots or releases and try to coordinate changes between downstream multiple repos. Maybe pulling in the snapshot, recompiling, running all those other tests. Of course, each of those downstream projects needs to be updated and tested in a specific order. Your repos all have like a graph of dependencies, and we need to follow that graph so that each repo tested needs to publish more snapshots that can be consumed further down the line, and so on and so on. Again, the further we get from our own repo, the longer the feedback loop is, and the longer it takes us to know with any degree of certainty that our change is safe. So, what's all this got to do with simplicity and complexity? Put another way, if we strive to carefully apply simplicity to our code and workflows, we can move faster and tighten feedback loops. The extra nimbleness this would bring will allow us to deliver the right features at the right time. Let's start from the end of the process and see how we can apply our ideas around simplicity to software development and testing. And the end of the process? I'm going to say that's deployment. Remember, we're trying to get to production as quickly and as safely as possible. In terms of knowing all the problems, pitfalls, and issues of our current deployment, the safest thing to do is to redeploy it with no changes onto the same fleet of machines it's currently running on. Now, if we did that, we'd never release new features. So although it's an interesting thought experiment, it's not really a helpful thing to say for this talk. But bear with me now. What if we only shipped one extra commit into production? Surely that's the second safest thing to do. And what could be simpler than pushing a single change? This is the path to continuous deployment, the second half of CI/CD. Charity Majors of Honeycomb has publicly stated how by adhering to very small changes in each release, they've been able to save significant engineering effort to the extent that their development and SRE team can be smaller than it otherwise would be. Now, I am sure there are plenty of people listening to this who are kind of shaking their heads at the idea of continuous deployment and backing away in horror. And in a way, they're right. After all, shipping a change into production isn't necessarily simple. But this is where our more nuanced view of simplicity and complexity come into play. Remember, we can choose where to place complexity. The choice of using CD means we've tightened up our feedback loops and we've made a release as simple as possible. It's just one change, but we've added complexity elsewhere. In order for a single commit to flow to production seamlessly, we need a lot of machinery in place. We likely want things like feature flags to be available to us, the ability to do stage rollouts, monitoring to be available, and an automated rollback strategy in place. We likely want to take people out of the loop as much as possible. That's why some people like to draw a distinction between deployed, that is, sitting on a machine but currently unused, and in production, that is, being used. And just because we have a single commit, we've not removed the need to do some testing and quality assurance. Maybe we can reduce the complexity of this testing since we can focus it like a laser on one aspect of our system, but it still needs to happen. I mean, on the flip side, we may choose to move more complexity into releases and batch up more and more commits. While this means that each release is riskier, sometimes it's the right choice to make. For example, when you're not going to be able to get everyone to install the latest release in a timely manner, maybe batching them up and doing fewer is a good idea. It's arguable that we need more monitoring and more processes in place to identify issues once code is in production with this approach. And it's clear that we'll need to do more post-release testing, especially since there may be weird interactions between components that haven't been pushed into the same environment at the same time at the same scale. Raise your hands if you have a UAT or user acceptance testing environment that actually matches production. Never seen it. At the very least, we still need the same level of monitoring available to us as when we do continuous deployment. The downside is that the path to production is less well trodden and is therefore less likely to be automated. Automating a release process takes the complexity of that process, experiences we have with issues arising as code flows through that process, and replaces it with a single command or button click. It appears simple. When we've not automated that process, we leave complexity lying around. As before, this might be something we consciously choose to do. I mean, perhaps it's not worth us investing the engineering hours into the automation for something that's seldom used. That's fine. But what we do have now, though, is a language that for us to weigh up the trade-offs and considerations. We can talk about what we're choosing to make simple, and we're aware that by making something simple, we may well be introducing complexity elsewhere. We can have a discussion about the cost of that complexity. No matter how often we choose to push to production, by the way, most teams do some kind of continuous integration. So let's think about that next. The purpose of a CI setup is to allow us to run as many automated tests or checks as we feel necessary to have confidence that known issues aren't present in a particular change. It's that definition of safety I was talking about earlier. The most common setup that I've seen is to use a pipeline. Typically, cheap operations are performed first. Things like linting or code formatting tests are often done early, as well as doing a build without running tests to ensure syntactic correctness of code. Next, tests of increasing size and complexity are run in order, with small or unit tests run first and the end-to-end test left for later parts of the pipeline. Often, stages fan out and fan in an attempt to parallelize work that can be, for example, I don't know, things like end-to-end tests sharded across multiple machines to speed them up. There tends to be a very simple approach taken too. Every change causes every part of the pipeline to run. Why do we do this? Because we're not always entirely sure what has been impacted by a change. It's safest to run everything. But doing so lengthens our feedback loops and worse, opens us up to false failures in the build. For example, when an unrelated flaky test fails, which lengthen feedback loops even more. I've seen some companies spend significant engineering effort and introduce huge amounts of complexity to trying to figure out which tests should be run in which order. Sometimes statistical modeling is used, or we front load the tests that have failed most frequently. I've even heard of people using LLMs to try and pick the tests. The problem with all these probabilistic approaches is they're not a perfect fit. They either under or overestimate the number of tests that need to be run, and working on this stuff can be incredibly demanding and not terribly rewarding. But what if I told you that we could make CI far simpler? What if I told you there's a way for us to exactly identify the subset of tests that a particular change will touch? What if I told you you don't need fan in or fan out in order to shard tests or other expensive operations properly? And what if I told you there was a way for us to start running tests before builds are even complete? What if your CI run was build and test everything affected by this change and nothing else? It sounds too good to be true, right? It's too simple. Well, I'm here to tell you it's possible. But the downside is we do this by shuffling complexity around. And we do that by making what can be an unpopular change. We switch build tool. Ultimately, our software projects are graphs. What do I mean when I say that? I'm talking about graphs as a data structure rather than a nice picture on a page. Build tools construct graphs of actions to perform. Actions are things like compile this, package that, or test these, and they typically take a set of inputs and produce a set of outputs. Those outputs often serve as inputs to other actions, and so on and so on. So, yeah, we have a graph of actions, a tree. Often that graph is topologically sorted and executed more or less linearly, but the graph definitely exists. If we know the build graph, we can use it to answer questions. If this file changed, what needs to be rebuilt? Let me show you some examples. Here is an example of a software project. If we change this file, then we need to rebuild and test only these parts of the graph. You can see that just by looking at it that it's true. If we change this file, guess what? We only need to change these, rebuild and test these pieces. And if we were to add a file, we only need to rebuild and test this subset of the graph. Finally, if we remove this file, we only need to rebuild this subset of the graph. There's a new class of build tool coming out, with Bazel and Buck being the prime examples, which make this graph available for querying, which make extensive use of that. Both of these tools offer the ability to cache outputs and to execute tasks remotely. The way that they do that is to inspect the inputs to your builds, including the tools and the versions of those tools to be listed in exacting detail. As you've guessed, switching build tools is an incredibly expensive operation. Worse, because it's a new tool, everyone's mastery of the tool will be relatively low. Operations that will be simple to an experienced user and going to be complicated to begin with. Workflows that work just fine with one tool will likely need to be updated. And I'll be honest, some things that used to be easy turn out to be a lot more complicated and involved. In particular, if you're using JavaScript and you're not going to have a good time with these tools. But combine the benefits of remote caching and builds, and you can do something really cool. This is the whole of Selenium's own CI build. As you can see, it's ridiculously simple. We run all the tests regardless of size, and then, because we've configured Bazel to not build anything not used in a test, we build the deployable artifacts, all the bits we will later push as part of a release. The tests are run for Java, JavaScript, .NET, Python, and Ruby across multiple different versions and multiple different browsers. In all, there are well over 2,000 tests, many of which are end-to-end and require us to fire up a browser. We typically get results back in under 10 minutes. How do we do this? The first step was to adopt Bazel as our build tool. This was not a simple task at all and required a lot of convincing people. One of the contributors, Alex, ended up writing an entire Bazel rule set to handle Ruby. The .NET integration is less than ideal, but our entire repo builds with Bazel. Adopting the tool was a choice about where we place complexity. For someone just focusing on one language, it's a lot simpler to use a native tooling for that language. But the advantage with this approach has been that any member of the team can contribute to any part of the project, and our installation instructions have gone from being impressively long to make sure you install Bazel correctly and have a working C++ toolchain on your machine. You don't even need a browser installed on your machine if you don't want it. The versions we use are encoded in the Bazel build. The second piece of the puzzle is remote execution. The Selenium project is supported by EngFlow, which make a remote execution grid with about 100 nodes available to us. This means we can run up to 100 tests in parallel at a time. Because Bazel is able to analyze the graph, and because we're using EngFlow's remote cache, when the CI build is run, only the exact subset of tests that are impacted will be rerun. Although we have approximately 2,100 tests in our repo, being able to use EngFlow means our build times can be very fast. We often see them come back in under 10 minutes, even for failed builds where we retry. A long build for us is 20 minutes. So we've absorbed a lot of complexity into the project by adopting Bazel, but that's made it simpler for everyone to build everything in the project without needing to have extensive setup instructions, and our CI builds look naively simple. It's a great example of us having taken the accidental complexity out of our build, just leaving the essential complexity behind, having that look like some noob's first attempt at getting CI running. So, thank you to EngFlow for making that happen. The choice to use EngFlow raises another way that we can choose to shuffle complexity around. We can choose whether or not we want to maintain the infrastructure we use to house our builds and run our tests. As an example, we can set up our own Jenkins or other CI servers if we want to. That gives us ultimate control. Or we could use something like GitHub Actions, Google Cloud Build, AWS Code Build, or similar. If you're a Selenium user, and you're here, so I hope you are, you can choose to run your own Selenium grid, or you can make use of a service such as Lambda Test instead. Within a single organization, it's common for teams to have their own repos. In fact, it's common for each project that each team works on to have one repo. From one point of view, this is incredibly simple. One repo, one project. But problems start to occur when we need to share things between projects. Perhaps we need to share some utility libraries or protobuf definitions. So now, or tests even, these get hived off into their own repos and their artifacts made available somehow. As we need to coordinate changes between repos, complexity goes up. Testing becomes harder. Keeping everything in sync becomes far from simple. The logical thing to do is to put things that depend on each other into the same repo. Taken to an extreme, this leads you to a mono repo, an idea of which I'm a huge proponent of. But there's no need to take things to extreme. Just right-size the repo so the things that need to change together are all in the same place. At this point, I'm sure a fan of microservices will claim that services are all utterly independent of each other. And I'd argue this isn't the case. The contract between them will need to be crystal clear. So although the implementations of the services may be completely separate, it's likely that the services are tightly coupled through the APIs. That coupling may be reduced effectively to zero by careful evolution of the API boundary, but that's a high discipline approach and it's hard to get right. Once everything is in the same place, making atomic changes and knowing that we've identified all the possible places that a change might impact, it's far simpler. The repo builds and its tests pass, change is good. So we can choose to spread the complexity of making a change across multiple different repos, or we can choose to accept the complexity of fewer, larger repos. The trade-off is the larger repos are harder to handle, and there may be significant political barriers that make it impractical. Should we adopt larger repos, we then need to figure out how we're going to build them. If everything uses the same language, native tool for that language may be sufficient. If we're dealing with a polyglot repo, then we might need a hodgepodge of different tools, or we adopt something like Bazel. The choices we make. But at least now we can make them consciously. I think we all know how hard it is to keep all the tests within a repo green. As repos grow in size, the risk of some tests somewhere within it failing grows. Most projects I know of block people checking in code when there are failing tests. It's one of the most frustrating things to happen is when a test that has nothing to do with your change blocks a merge. Even if you're using remote builds and execution, it's possible to have a test start failing and then continue to fail, causing everyone's builds to be blocked until it's fixed. When you're using a build tool that exposes a build graph, it's possible to query that graph and ask it for the subset of things that need to be built and run. That means that it's possible to land a change in the tree when your change is good, even when an unrelated part of the tree is red. It makes it far nicer to live in that place. In the Bazel world, the tool I've used for this is called Target Determinator, and there's a link to it here. The next evolution of Selenium's own CI could likely use Target Determinator. However, since things are sufficiently fast, everything is related, and we only ever build with the Enflow cluster, and we make use of caching, I don't think we need to take this step yet. We're thinking about complexity again. So in summary, we've covered a lot of ground in this talk. So before I finish, let's get the ideas lined up and clear. The first idea is the goal of software engineering is to get a change into production as quickly, safely, and as cheaply as possible. One idea that flows from this is that we want our feedback loops to be fast. The sooner feedback arrives, the easier it is for us to make fixes or change course. Another idea that flows from this is that simple changes are safer than complicated changes. Practically speaking, this means that we should push to release as often as possible, since that means there are fewer changes being made live at the same time. It makes testing so much easier too. But this starts a discussion about what we mean by simple and complex. We started with a simple definition, that simplicity is just a lack of complexity. But we made this definition more useful by talking about accidental and essential complexity. Any single problem or task has some essential complexity that needs to be addressed. Accidental complexity is additional complexity, the resolution of which doesn't actually go to solving the problem or task. Of course, the definition of simple or complex has an element of mastery of the domain. And if you're new to a particular kind of problem, things that seem more complex than they might be to someone experienced in it. I'm sure we've all known that occasion when we're working with someone steeped in a project and they just seem to know what to do. That's what I mean by mastery of a domain. Finally, once we're aware of the relationship between complexity and simplicity, we can choose where we can place complexity in our system. Do we spread it out evenly, hoard it in one place, or do we push it away from us entirely by picking services provided by others? So here are those final details left in a single place for you to read at your leisure. I hope this talk has helped provide you with a way of thinking about problem solving and a way for you to apply it. Thank you all very much for your time and attention. It's been an honor to speak with you all. And I will now hand back to Manoj because I think we may be just a little bit over time.
Thanks, Simon, for insightful session. I'm sure you all learned from all your experiences. Definitely complexity and simplicity, right? I think there's a lot of questions actually, and as you rightly said, we are actually out of time as well. But I just wanted to touch upon a small thing. One of our very good friends, Naresh Jain, also asked this question. To put it shortly, is minimalism one aspect of simplicity?
Certainly, that's one way of looking at it. I think if you take a look at a sort of complicated solution, it will have stuff piled all over the place. If you take a look at a simple solution, it will have the minimal amount of stuff in one place. Sometimes, however, minimalism is trying to pretend that you can ignore some of the essential complexity of a problem. So you're trying to just cut away bits and pieces and then ignore that. And that means your solution isn't actually complete. It just looks simple rather than being simple. Does that make sense?
Does. I hope it does for you as well, Naresh. Thanks for asking the question. And Simon, thank you again so much for your time and delivering such an insightful talk to everyone. And thank you everyone who has joined us for this keynote by Simon Stewart. The session is recorded and it will be available in YouTube shortly right after the conference. I hope it's been a great start with a great learning from the man himself. And I'll let you enjoy the rest of the day with so much more insightful sessions coming for the day. Thank you again.
Thank you, folks. Cheerio.
Thanks, Evan.